So welcome everyone to the presentation on Apache Spark. I had sent in a short description of the talk a while ago, and I had updated it since, but it didn't make it onto the website. So thank you very much for showing up, even with a very technical description. So basically, Apache Spark has had a lot of people are talking about Apache Spark, how they're quite likely to be replacing Hadoop MapReduce and all the things that become possible. And I think the thing that's really interesting in the context of today is how much it makes possible from a native Python perspective. So my name is Johannes. I'm originally from Germany, now live in Cork, work as a mobile developer, but hoping to professionally get into the data analytics space. So maybe just one slide to start out, because I think it's one thing that there's often some confusion about, which is, so here we have like a little matrix on the left, and on the lower side we have the local aspects, and on the upper side we have the distributed aspects. And then we have parallel programming on the left and concurrency on the right. And I think the distinction isn't made very clear, so I'm still struggling, so if anything is wrong on the slide, just shout out. But I think it's a really important distinction, because they're such different things, and we always throw them into the same bucket. So basically the distinction is that parallel programming is deterministic. So we have some kind of mastermind that has data and wants to do something parallel on it, and it organizes things and controls and orchestrates. And with concurrency, we actually have multiple actors that are all doing things at the same time. And so I think in almost all ways, parallel programming is much easier than concurrency. So if we, so on the lower side, if we have parallel programming, we have things about if our code has side effects, then it's more difficult to parallelize. On the right-hand side, all the usual fun of concurrency. We have locks and deadlocks and a lot of logic that has to be in place. And then if we go to distributed model, on the left we have solutions like Spark and MapReduce that allow us to manage parallel programming. And I think on the top right, probably the best paradigms that I'm aware of anyway is the actor model of Erlang and Akka and Pika. So basically all of this is hard. The right-hand side is a lot harder than the left-hand side. But all of it kind of falls outside of our sequential thinking, where we just go, I want to do A and then I want to do B. If we have a cluster with 1,000 nodes, that kind of thinking can get us into hot water, and that's where Spark can really help. And then I have on the right this idea of functional programming. I'm a huge fanboy of Haskell and functional programming, but not for its own sake. I think it can help tremendously in those spaces that I've shown on the left. And arguably, Akka and Erlang are functional approaches, and definitely Spark has some very functional elements. So can I just maybe show of hands, who of you have heard of Spark before? Okay, cool. And who of you have worked with Spark? Okay, a little bit of a difference there. So just a short overview of what Spark is. So basically, if you have very big data that you want to run analyses over, you will have to do so on more than one machine. And if you have more than one machine, you have a cluster of some sort, and then you need some software to manage the cluster, to split up your data, to send it out to nodes, to make sure that if nodes fail or if something unexpected happens, that you recover from it, and then to get the answers back. So for the last, I don't even know how long, 10 years, MapReduce and Hadoop have kind of filled that space very successfully. Google came up with it, or Google were the first to implement it on a huge scale, and then Hadoop was developed and open sourced. And then there's this whole Hadoop ecosystem that does things on top of on top of Hadoop, like for example MapReduce, which is one algorithm in the Hadoop ecosystem. So Apache Spark, the idea is that we have a general engine for large-scale data processing. So if you have huge data and you want to process it in a parallel manner, then Spark may be the right thing. I'll come to the differences with Hadoop in a moment. So I just want to kind of give a quick overview. So the idea is that you have multi-stage in-memory processing. So multi-stage means you define something and then it gets executed in multiple stages. And in-memory in this case means that Spark makes use of the node's memory. So in Hadoop, everything is very much based on in vanilla Hadoop, everything is very much based on the file system, the Hadoop file system, distributed file system. So whenever there's a Hadoop job, Hadoop only has two stages. It has MapReduce, has map and reduce, so it's fixed. So it reads something from disk, it does a map, it does a reduce, and then it writes it back to disk. So Hadoop MapReduce has two stages. Spark has as many stages as you'd like. Hadoop MapReduce does a lot of its logic through reading and writing to and from disk. Apache Spark has the ability to cache in memory, so there's a lot of speed up potential there. Coming back to the multi-stage, Apache Spark is a lot more useful for iterative algorithms. So one space where that came up, so MapReduce is still really good if you just want to take data, you want to transform it in those two stages, and then write it to disk. So in some senses, in some use cases that Google and others have had, that's really good. But in many cases, for example, the PageRank algorithm, that's quite iterative. So if you have to do things over and over again over the same data, then you keep reading from disk, writing to disk, reading from disk, writing, and that, so you lose a lot of performance because you do a lot of disk writes and reads. Apache Spark offers some really nice high-level abstractions. So that's kind of where the functional aspect of it comes in. And it's quite extensible, and it comes with quite a nice set of libraries, and I'll talk a bit later. So it has a very performant SQL-like interface, which is Spark SQL. It has a streaming capability, it has a machine learning library, and it has a graph analysis engine, all built on top of the core Spark. So and then seeing how, that's a tiny bit missing here. Let's see. So a little example of what Spark looks like. So this is completely Python code, and I think that's kind of the big thing. So a lot of the jobs that you might want to do, they might be perfectly well suited for MapReduce, but up until now it has been, in many cases, quite a pain to run Python jobs on top of Hadoop MapReduce. And so here we have a completely native interface with Python. So the first thing you do is you create a Spark context. The Spark context will contains your orchestration, so it will take care of partitioning your requests and things like that. Then the next thing is you create an RDD, and an RDD is a resilient distributed data set. So what that means is that we have, there's two modes that we can get data into Spark. One is we move it from our local machine, just any type of collection, a big list, anything that's iterable. Or we pull something from a Hadoop file system. So those are kind of the two major data sources that we can do. If we pull it from the local machine, it needs to be partitioned. So then your Spark context will say, oh, I have 50 machines, so I'll partition it this way. If you pull your data from HDFS, then it's already partitioned by nature of how HDFS has stored the data. So those are the two main ways. So in this case, we have two local files. We create RDD1 from text file 1 and RDD2 from text file 2. And then, do we have a laser pointer? Okay, thank you. What's that? Into where? For this laser point? No, it's okay. That's fine. I just need the pointer. So we define a perfectly normal Python function that says split line, and so our lines, they are to be split by the pipe character into a key and a value, and then we return a tuple of the key and the value as a number. So it doesn't get much simpler than that. So text files by default, they will be iterated over by line. So let's say the file has 1 million lines. Let's say Spark partitions it into 5 partitions. Then each one has 1/5 of 1 million lines. And then what we do next is we say for RDD1, we want to filter the lines, and we want to make sure that after the filter, we want to filter out all the lines that have an error in it. So we say filter by line, only pass it through if it doesn't have error in the line. And afterwards, we want to run the split line function over each line. So if there was an error, then the int val would fail, so that's why we filter them out. For the second distributed data set, we say there are no errors in this data set, so we want to just map it, but then the keys can occur multiple times, so we want to add all the values by key. Let me just show you the files, what they look like. So this is file 1. So here all the keys are unique. So we have key 1, key 3, key 5, but key 5 has an error in it. And the other file has key 9, key 3, key 3, key 3, key 1. So you can see that some keys are occurring multiple times. So we need to reduce all those lines to get one value per key. And then what we do afterwards is we say we want to join on A and B. So no, we want to join A and B, and what this does, it's an inner join. So it takes all the keys that are, it only will output the keys that are in both data sets, and it will join them into a result set. So not too dissimilar from a SQL join. And then we want to take 10 values of the result. So the result is key 3 from the first data set we got 50, from the second we got 30, key 1 from the first we got 20, and from the second we got a sum of 60. So this is a very simple example, but I think it already shows, so these files could have been a terabyte, and you could have had 1,000 cluster nodes. And so the cluster would be set up probably with Yarn, the same. So basically for Spark, you would use a very similar environment as you do for Hadoop. So you quite likely have a Yarn cluster manager set up that would work with the clusters and your Spark context. So in this case, you wouldn't use a local context, but you would use a remote context and tell Spark where to get to how to get to the cluster. But so you have this sitting on your local computer. You change maybe the test file to hdfs:// and then you've just done a filter MapReduce by key join over 2 terabytes on 1,000 clusters. So I think that's really there's 2 big things here. One is that you're able to build a generalized tree. Let me just show you that. So this is roughly what it would look like. So what Spark does, it takes your all the map and filter and join and all of these things. Those are transformations. It takes those and builds a tree out of them, a direct graph, and then it optimizes the graph and deploys it to the cluster. So here we have our source RDD. It gets mapped to something else, and then so this is group by. It should say reduce by. So that's where we added all the values by key, and then we have our second source data set. We have a map over it. Then we have a filter, and then we join the 2 data sets together. So obviously this is a very minimal example and not particularly interesting, but actually if you have a terabyte of data, you'd probably be happy that it's not particularly interesting. So these trees can get arbitrarily large. So there's no limit on, well, probably there's some limit, but basically you can just put in your algorithm how it fits into the primitives that Spark provides, and then Spark will do all the optimization for you. So for me, personally, I like to compare it to like a SQL database. So you put in your declarative query, and then a lot of magic happens, and then you get your result back in like 0.1 seconds. And you don't, like I don't know all the magic that goes on in a SQL optimizer, and it does all kinds of heuristics and optimizations and internal caching, but I don't care. I just query, and I query in a very declarative language, and I get my result back. And I think that's quite similar. Obviously, you have to have some idea what's going on, because if your query takes 10 hours, you have to do stuff. But otherwise, it really gives some peace of mind to be able to be quite declarative in what you're trying to achieve. So let's see. So just to come back to the comparison between Spark and MapReduce. So in MapReduce, as I said, you have your data source, you have your map phase, you have your reduce phase, and your data sync. That's always looks the same. If you need to do something more, then you put another one here. So then you go from the sync to the source. And so there's a lot of disk writes and a lot of disk reads. With Spark, we have arbitrary operator graphs like this one here, and they can get, could have thousands of nodes. And what Spark will do is to optimize and say, oh, I've got 3 maps in a row. I can fuse them together, or I can change the order of operations because of how it has defined its basic building blocks. So if we go back up here, so I've marked this stuff green, and I'm not sure if it's clear to you why I've marked it green. Actually, what we're seeing here is 2 things that look the same but are actually different. Everything that's not green is happening on my local machine, and everything that is green is actually happening on the cluster nodes. So I think that's another nice thing of how they've put together the Python client, that you don't even notice that you're programming in 2 languages on 2 different machines. Well, I mean, they happen to be the same language, but they have almost nothing to do with each other. So basically you have the things that are highlighted in green, they're operating in a completely different context, in a completely different machine, on different data sets. And the stuff that's not green is happening on your local machine, but you don't even know, because I think it's really well put together. Let's see. So when you put these together, Spark will wait until you call an action. So take, for example, is an action. Take is something where you actually say, give me the values now. And Spark will build this tree lazily, and it will wait until you call an action before it will actually start the query. So that means you build this huge graph lazily, nothing happens. So if we go back to the example, up until this point, basically nothing has happened. You've just built an abstract representation of what you want to do. And only when you issue this command here does the whole engine optimization, orchestration, cluster thing happen. As I mentioned, use of large memory. So Spark, it can deal on disk if you have very large data sets, but its strength lies in memory processing. So the ability to cache results, and then you can come back later to it and it's still there. So that's a big plus. And I think the native Python integration is really strong. So just a couple of words about the resilient data sets. So we can see, basically you have your data set and it's partitioned across multiple nodes, and then you have this graph of RDs that are linked to each other. And the one thing that happens in distributed computing is machines fail to come back, like to respond back to you, and then you need to deal with that somehow. And the beauty of the Spark model is that because it has built this directed acyclic graph of operations, if one little node, so if this node here fails, Spark knows how to reconstruct that without starting the whole query over again. So it says, oh, I can see it took data from here, from there, and I know what operation it did on those nodes. So it can just reconstruct this, and hopefully these results are still cached. So it could spawn up a new node and populate that node with the data that was lost in a very, very short amount of time, because a lot of caching and a lot of high-level logic is going on. Sorry, that was not too far. So caching I already mentioned, and there's also extensions to the RDD. So an RDD by default is just something that's iterable or partitionable, but you can add, for example, schema information, which means you have a table with column with attributes, and then you can, that's what actually Spark SQL is based on. So you can have a distributed SQL-like syntax that's a lot more performant than some of this SQL pseudo SQLs that we've seen on Hadoop. So these are the lazy transformations that you have here, and this is really where you can see that there's really a functional thinking behind it. So anybody familiar with functional languages, and to some extent Python has some of those. So you can map, so you can take your values and create values that have mapped all the values by a certain function. You can filter, you can take a sample, that's quite interesting. So you just say, oh, I just wanted a simple sample, a random sample of my 1 terabyte file. You can group things by key, you can reduce by key, which we use to add up the values for the same keys. You can join 2 data sets. So there's loads of these here. And then on the right, we have the actions, which actually trigger the actual computation. So on the left, we're just building an abstract graph, and on the right, we tell Spark what to do with the result. So we can save it to a text file or a Hadoop sequence file. We can just count how many results it got. We can collect, which is just all of it. So that's how these transformations and actions look. And then, aware that my time is limited, but so just to give you an idea of the life cycle of an RDD. So as I said, you can either create one from a local collection, and then it will have to be sent out if it's big, or you can create one from a Hadoop dataset that's already living on HDFS. Then you lazily combine the RDDs into a graph like this. At the end, you call an action on it, which kind of triggers the tree to be evaluated and optimized and sent out. And then loads of things happen. So the directed acyclic graph is constructed. It's split into stages. So stages are as long as you have all the source data within an RDD. So you can see here we just have a horizontal arrow, and here we have another horizontal arrow. As long as that's the case, this is one stage. But as soon as we need data from, to cross and be collated, then we need to create a new stage, because we first need the first thing to finish before we can start the second task. Then the tasks are launched by the cluster manager and then executed on the local machines, and at the end the results are either stored on the HDFS machines or collated back to the Spark master. Okay, so I think Spark SQL is actually really, really cool, because it enables something that, to my knowledge, hasn't really fully come to fruition on Hadoop, which is just ad hoc queries on really big data. And many of the approaches anyway are not really real time. So you have quite a long wait time, which then isn't really an ad hoc query. So then you need to define your reports and things like that. So Spark SQL really promises, or delivers, and also promises really good performance on distributed schemas that you can join and select from. Spark Streaming uses micro batches, so it just takes your data that comes in and makes it into batches that are a second's worth, and then it moves it through the tree that we've seen before. So if you need microsecond response time, maybe not the right thing, but for everything that that where you have like half a second or a second latency, this is a really performant and a really great option. And the nice thing is you can reuse your business logic between batch processing and stream processing. So you don't need to write two things that then give you different answers. The machine learning library, talk of its own, so you have everything random forest, logarithm, linear regression, logistic regression, all your standard tools are there, and you can really run on it. And then you have the graph analysis that I haven't done much with, but I think it's also really powerful. Okay, so I think I have 5 minutes left. I wanted to give a little demo, but I guess I've talked about the code already a little bit. So, a couple of takeaways. So it feels like native Python. So you don't feel like you're writing stuff for other nodes and how do I get it back and do I have to cast it to some C struct or something. So you just write Python code. Really nice API. It adds the awesomeness of a cluster or not. I don't have a cluster at home, but even things like processing on 4 cores or 8 cores or 12 cores isn't always that straightforward on Python. So even just leveraging your little mini cluster you have in your machine is already a real bonus. Comes with batteries included, so it has a standalone environment that you can use, and which works really well. And you can have all these things those are already fully integrated, the machine learning, the SQL. And I think probably one of the bigger points, you can use it for exploratory programming. So you can go right now, if you're on your computer, or on Monday or tomorrow, you can just write everything that has to do with data processing using Spark on your local machine. I don't think there's a huge overhead. And then if at this later stage you go, oh wow, I need this to be twice as fast or 5 as fast, you just add more nodes and it automatically works. So it has so little overhead in terms of what you have to consider and think about and so on, that I think you can just write anything that's dealing with reasonably large data. You can write everything in Spark on your local machine. And then whenever the need arises, you can stream it, you can batch it, you can run it on 10,000 clusters. Which brings me to my next point. So these are a couple of options to start. So there's the Spark distribution, which has the interactive PySpark interpreter. So you can interactively interact with your cluster, which is actually pretty awesome. So you can say, please load this terabyte file, and please now cache that and tell me how many items are in it, and then now give me the first 10 or something. So it's fully interacting with like this huge Mesos yarn cluster. Another option is to use Docker Spark, which is a distribution, a Docker image for Spark. It's available on the Amazon EMR. Is that the machine? Yeah, so it's available as a capability on the Amazon machine learning capabilities. And there's also a setup for a MOOC, which was the scalable machine learning. So it's a Vagrant VirtualBox and notebook, which I've running here. So I think that's also a really nice way to start. So you just have your notebook, and then you can just evaluate. So for example, if I say, oh, I've just built this, so this is the same source code that you saw before. I've just built this graph. So now I'd like to analyze what the graph looks like. So then I can say to debug string. The resolution isn't great. Let's see. So then it shows me the graph that it has built. Obviously this text representation isn't very powerful. I'm not sure if there's a visual representation of it, but it kind of gives you an idea. So you can see it read a text file, then it put it into partitions, or it mapped over partitions, it reduced by key, did a join, and then, what does it do? Yeah, so I think it's really doable to start using Spark today, tomorrow. Basically, all you need is one of these environments, either the local interpreter, Docker, Amazon, or the Vagrant VirtualBox, and it takes literally 5 minutes to get started. And yeah, so then you're golden. I don't think I have time for questions, but are there any questions? Yeah?
Just like, ask what platform support is a JVM?
Yes, so Spark is written in Scala, and it's running on the JVM for whatever running on the JVM means. So the nodes, the cluster nodes, they're running JVM, but the Python is actually executed in its own Python environment. But the cluster nodes, they're written in Scala and they're running on the JVM.
Thanks.
The whole thing is written in Scala, but thankfully we don't need to worry about that. Yeah?
There's a bug somewhere deep in. How do you debug that?
Okay. Yeah, that's a very fair question. So part of it is, let me just disable this. So, and that's a little bit of downside of Python, that you don't get very good compiler support. So let's do this. So if I forget the int, so I'm just splitting on the pipe symbol, so now I have two strings instead of a string and a number. Well, actually, with the plus it might work. Let's see. Because I think I ran into that before. No, that didn't work. So let's see. So basically, it's a little bit tricky. So I'm not sure if I can demo. I can show it afterwards. But basically, what you get is you get an error message from your cluster machine saying my Python failed, and then it gives you the stack trace of your Python. So it's okay, but it can probably be improved quite a bit. So it's readable enough. So it tells you, this is the piece of code and all of those things. But debugging, the nice thing about parallel programming is that debugging is a couple of magnitudes easier than concurrent programming. But yeah, I'm not sure I have the full answer for that. I haven't really run into huge issues because a lot of if you take a lot of the time, the things you pass in here will be pretty small. So a lot of your logic actually lies in your Spark primitives, and those are, those are pretty well debuggable, because that's the optimizer that says, oh, what happened here? So the fragments in here, in the use that I've made of it, have been pretty small. So I've not had thousands of lines running it. But yeah, I think that's definitely a very valid question. Okay, cool. I think I'll have to wrap it up. So